So good afternoon, everybody. I hope everybody is okay, is taking care of yourself and everybody else. So continuing our seminars, today we have the pleasure to have Marco Muñoz Gutierrez. Marco he got a PhD from Instituto de Astronomia at UNAM, Universidad Autónoma de Mexico. And he has been here in Brazil in our group for a couple of years as a postdoc from FAPESP. And then he moved on to Taiwan for a few years. And right now he is going to Chile. So it's coming closer to us again to work on the Centro de Excelência Astrofísica y Tecnología Afines. And so it's a pleasure to have you here, Marco. And so you can start your presentation, please.
Thank you very much. Thank you very much, Tom. It's a pleasure for me to give a talk again at the group. So yeah, I think I don't have a pointer, but I will try to be clear. Yeah, I will try to talk about this puzzling population in the outskirts of the solar system, the so-called extreme Trans-Neptunian objects, which are a group of very interesting objects that seems not to have a very clear origin and seems not like they shouldn't be there where they are, according to our very fine understanding of the early evolution of the solar system. So they are a pretty interesting group to study and to put to test all these theories. In particular, I want to talk about this because the number of extreme Trans-Neptunian objects is still very limited. There are very few known objects in this population, and that's because they are very far away and they are very difficult to detect, even with the most sensitive surveys that we have done so far. And I'm involved in this with the study of this population because in our group in the Academia Sinica, some colleagues from ACIA found a new object in this family that it's also besides much more interesting because of its physical properties, not only its orbital properties. So to start, it's good to have a more or less clear picture of the structure of the Trans-Neptunian region as far as we understand right now. So in this plot, we are seeing the current distribution, more or less current, up to 2019, of all the objects known with semi-major axis larger than that of Neptune. We can see the distribution of the different populations in the Kuiper belt. In red, we can see the classical objects. In white, the Plutinos, centaurs in orange, and other comets in blue. We can actually see that the most internal orbit plotted here is that of Jupiter, and we can see the Jupiter Trojans. Just to understand that this is a very it's a very well-known population. It's the distribution is pretty well determined, and actually it's pretty well understood how it come to be. So if we see the distribution of some of these objects in the polar view and ecliptic view, we can see that this belt of objects beyond Neptune is not really a cold belt. It's not as was expected from the early works that proposed the existence of this belt of objects, that it would be very, very flat, very, very calm, objects with very low eccentricity and very low inclination that could be only the remnants of the protoplanetary disks that were not able to accrete to form larger things and they basically, it was expected that they were basically a belt of debris, of icy debris that could be the origin of short period comets. But very quickly, it was found that the distribution of this belt and all this population beyond the orbit of Neptune is actually much more excited than it was expected. So we have a family called the classical belt, and in particular the cold classical belt, that is actually very similar to this original idea, to this original conception of how it should be the Kuiper belt. It's very, it contains very cold orbits of very low eccentricity and very low inclination. But all the other families, the scatter objects, the resonant objects, and the hot classical ones are all much more hot, dynamically hot than their counterparts in the cold classical belt. And the distribution of the Kuiper belt, of the objects in the Kuiper belt, it's pretty well understood, and actually some models have been done to account for the theoretical unbiased distribution of objects in the Kuiper belt, which is, for example, the L7 model from Petit and Gladman that you can see here in the plots from the right. The phase space plots of semi-major axis versus eccentricity in the top panel, and the semi-major axis against inclination in the bottom panel. So we can see here that this supposedly the bias object, which considers all the possible observational biases in the observed population, contains a lot of classical objects in black, a lot of very well populated resonances, in many resonances, not just the Plutinos in the 3-2 and the Tuotinos in the 2-1, but actually many of these resonances are considered to be very well populated. In particular, this 5-2 mean motion resonance with Neptune, it's considered to contain a very important population of objects. Here I'm plotting also the 34 largest Trans-Neptunian objects observed up to at least 2019 also in green. And that's because we use that population together with the L7 model to study the contribution of these large planetesimals to the injection rate of Jupiter family comets in 2019. But that is not what I'm talking here. What I want to point out is that the origin of this structure, this very rich structure that we can see in the phase space, very well understood based on the theory of the early planetesimal driving migration of the giant planets. And that's because if you consider that you have a planetesimal disk from which the giant planets are forming, are accreting, the interaction with the leftover planetesimals, which are massive, at least importantly massive, and in the most recent theories, they are considered to be at least some thousands of objects of the mass of Pluto. So the interaction of these massive planetesimals with the giant planets would produce an interchange of angular momentum that when the giant planets move this interchange the angular momentum with these leftover planetesimals, they migrate outwards if the planetesimals is sent inwards in the solar system. And then Jupiter, which is the main ejector of planetesimals, moves slightly inward because he's losing angular momentum. But not all the planetesimals are ejected. Many of them are implanted actually in what is now the region of the Kuiper belt, and in particular the hot population and the scattered disk. It's formed by implanted objects from this interaction in the early solar system. Of course, we know that Prino Malhotra since the 90s used this idea of the planetesimal driven migration to explain the peculiar orbit of Pluto, which with this model of resonance sweeping, which predicts that while Neptune is migrating outwards, its mean motion resonances are trapping in their way objects and in this case the 3-2 mean motion resonance traps Pluto, and during the outward migration of Neptune, the mean motion resonance also move outwards, and then the eccentricity of Pluto is increased when it's migrating together with the resonance. And in this way, Neptune is able to trap a lot of objects in the mean motion resonances, in particular the 3-2 and the 2-1, but also in many other resonances, which are intermediate and beyond the 2-1. And this explains the large number of objects that are trapped currently in these particular locations. The theory also explains why the eccentricities of these objects are large, but it's very hard for the resonance sweeping alone to explain the high inclination of many of these objects that are trapped there or implanted there. So all these early ideas more or less find their culmination in the NIS model that suggests that the early configuration of the giant planets in the solar system was much more compact than it is today, and that Jupiter and Saturn were actually very close to their 2-1 mean motion resonance. And when they start to interact with the leftover planetesimals, these slight movements of this initially a smooth migration, it's perturbed and it's accelerated when Jupiter and Saturn cross their 2-1 mean motion resonances, and this basically disrupts all the disks of leftover planetesimals, and many are implanted in the current Kuiper belt. So this model show that it's possible to explain many of the characteristics of the outer solar system with this idea of the early migration plus an instability between Jupiter and Saturn. So Nesborny in 2017 made a very complete simulations to actually account for the origin of short period comets from the outer regions of the solar system, basically the Trans-Neptunian region, and in particular the scattered disk. So Nesborny used millions of particles in the test particles and this model of early migration of the giant planets as far the best model that they have after several years of experimenting and constraining the parameters of the migration. And they found they basically look for the ingredients that are necessary to reproduce the observed structure in the outer solar system. So one of the important ingredients in these first panels, shown here in the panel A and the panel B in this figure, it's the galactic tides. It's well known that you need to include galactic tides in order to form an Oort cloud. Otherwise, the ejected planetesimals are simply ejected and they never circularize, and they never are isotropized in inclination as to form a spherical structure around the sun. So the first ingredient, of course, is the galactic tides. Many people have suggest that the origin of these triangles that I probably here I need to do this. These triangles here that are far from the main concentration of the most distant objects known in the solar system are originated by a stellar passage, by a stellar encounter that of course perturbs objects in some objects of this cloud of ejected planetesimals or almost ejected planetesimals. And if you combine the two effects, you have a good representation, but still not as good as you would like for, in particular, for these very distant and very extreme objects. So the dynamical forces that are acting in basically all the region up to the R cloud are more or less well understood. In this diagram, which is a little bit, it's a kind of cartoon of the forces, as a schematic diagram of the forces that are acting on the small planetesimals in the outer solar system. We know that for large semi-major axes and large perihelion distances, only galactic tides are of importance, because these objects are basically detached from perturbations from direct perturbations from the giant planets, in particular from Neptune. They can suffer some secular perturbations from planets, a combination when the semi-major axes are smaller, and these perturbations move the object basically in the vertical direction. This means to increase their perihelion distances. When the objects are closer in perihelion, the planetary scattering is much more important. And this planetary scattering basically maintains the perihelion distance constant, but the semi-major axis is always moving in a random walk and basically increasing in with every encounter with the giant planet, in particular Neptune. So the first interchanges of energy in the first passages moves slightly the same major axis, but the next ones moves the same major axis more and more until the objects are essentially ejected. And very close to the planetary region, with perihelion distances up as low as 30, which is the same major axis of Neptune. Basically, there's a combination of the planetary scattering and the mean motion resonance that are very important and move the objects, all this region, in many directions. When the semi-major axis it's low, but the perihelion it's above certain level, only isolated mean motion resonances can increase the eccentricity, essentially, of objects. And there is, besides this inert zone, where no effect is actually very important, and the transport time in this region, is this blue region, is extremely large. So objects that are or that were insert or that reach that inner region for some reason or another, can remain there basically for the age of the solar system without experiencing any perturbation from any of the forces involved here. And this is the region where the most extreme Trans-Neptunian objects are located, and that's what makes them out of place in some sense. So we, in 2021, a paper that we in which we studied the dynamics of the dwarf planets, actually the dwarf planets that we use for as perturbers in our work of that explores their contribution to the Jupiter family comet origin. We actually explore the diffusion times of objects basically in the region of the Kuiper belt that it's in most close proximity to Neptune. So again, in this plane of semi-major axis versus eccentricity, we plot the diffusion parameter of the test particles, of 34,000 test particles, obtained by frequency analysis of Laskar, for particles that are randomly inclined between 0 and 50 degrees, which represents more or less the inclinations of Kuiper belt objects in this region of the phase space. And then we calculate the diffusion time of the average diffusion time of particles as a function of their perihelion. And we find some interesting results that are in agreement with what is known for objects in the Kuiper belt. So in this figure, I'm showing the stable fraction of particles that have a diffusion time above a certain threshold. So essentially, the curves tell us that the objects below, or the fraction below the curve, it's stable for more than the time indicated by the color. So in essence, for example, for objects with a diffusion time of 5 gigayears, we find that above for a perihelion above 40 astronomical units, more than 90% of the particles will remain stable for more than 5 gigayears. So essentially, all the population with perihelion above 40 astronomical units is stable over the age of the solar system, and the fraction, of course, it's much less for smaller diffusion times. So and this clearly increases with perihelia. So what we can get from this plot is that the larger the perihelion, the larger the stability time of particles, and this of course decreases very quickly because particles that get close to Neptune are very quickly ejected in very short time scales. So we can lose half of the population in less than 1 gigayear, for example, for objects that have a perihelion around 34 astronomical units. So what is the perihelion of the most extreme Trans-Neptunian objects? We can see here in this plot from Trujillo and Shepard when they found a second very large perihelion object, 2012 VP130, that it's actually quite similar to Setna, founded 10 years earlier by Mike Brown. Yeah, as far as I remember. So up to 2014, these were the only two objects known with very large perihelion distances. Because of course, the larger the perihelion, the most difficult it is to find these objects in observational surveys. But the curious thing, besides that, is that objects with smaller perihelia, but still with large semi-major axes, in this case above 150, seems to be clustered in the argument of perihelion of their orbit. So essentially, their perihelion points are very close in direction in the sky for all these objects with very large semi-major axes. But how could this be? If we consider only the 4 giant planets of the solar system, and we integrate the evolution of this kind of objects with large semi-major axes, large perihelia, they essentially remain unperturbed for secular timescales, for gigayear timescales. In this plot from the left, we can see the evolution of the argument of perihelion, which basically circulates over a period of 2 gigayears. Well, in this case, Circulation period is much less, 500 mega years, but the important thing here is that the argument of perihelion actually explores all the values. So there is no we only consider the four giant planets of the solar system. There is no reason why the argument of perihelion of all these objects would be clustered around zero in this case. We have made some simulations also, considering, in this case, 200 identical initial conditions of 2012 BP 130, and integrating over 1 giga-year with the four giant planets only. And we find that the evolution of these objects, as detached as they are, it's pretty well behaved over very large timescales. But if you include an external perturber, in this case, in the experiments of Trujillo and Shepard, they include 5 Earth masses planet at 210 astronomical units. You can actually constrain the argument of perihelion around the value that you are looking for. So this was first indication that some of the possible existence of some external perturber in the outer parts of the solar system that could potentially explain the clustering of all these extreme trans-Neptunian objects. Of course, this is it's important to keep in mind that this is a small number of statistics. So still, this clustering could be artificial or could be an observational bias. But if it is not a possible explanation, it's to keep in mind it's the existence of an additional massive perturber. So it's easy to understand why these objects remain there for the edge of the solar system unperturbed, given their distances and their perihelia, and the yeah the size of their orbits and the faraway distance from which they interact with the giant planets. So they didn't move. So how did they get there? In particular, that's the important question. We can, from what we saw before, we can understand the structure of basically all the objects in the Trans-Neptunian region, the classical belt, the scattered disk, the centers, the resonances, but the detached Kuiper belt objects are there apparently without any clear origin. And it's pretty well concluded that secular chaos and the early planetary migration, it's unable to produce the whole structure, basically the origin of these detached objects over the edge of the solar system. So there seems to be additional ingredients to this story. This plot only gives a perspective of the sizes of the orbits of these most extreme objects and how they are pretty well aligned with their perihelia pointing more or less to the same direction. So Batigin and Brownquist, who were the ones that proposed with more precision, with more restriction, much more better restrictions, the possible orbit and the possible characteristics of this external perturber, now called Planet 9, made this review of the Planet 9 hypothesis in 2019, which is pretty well explained, and it's pretty interesting. And by 2019, we have a larger family of objects, a slightly larger family of objects in these extreme orbits. So here he is showing the apsidal confinement of objects in the longitude of perihelia, now not argument of perihelia, but longitude, and of the longitude of the ascending node. Also the and this right hand side plot is showing the direction of the perihelia of many of the orbits and how they more or less are confined to a particular region of the sky, which is pretty interesting. As we saw, this is explained by the existence of a massive perturber in the outer solar system. In 2021, Brown and Battingin constrained much better in the possible orbit of this planet, but also the orbital parameters and the mass. In this plot of that I would like to point, in this plot of the right, they show the space of parameters that still could hide an additional perturber in the outer solar system. So essentially, it explains all these colored lines give one or another constraint uh, for the existence of planets more or less massive than that. So the green line indicates that the planets with mass below the green line would not be able to clean their orbit, and they will therefore call dwarf planets. Planets that were originated with semi-major axis larger than 1000 basically would be unstable in the Bird cluster of the sun. So therefore they couldn't be present now, and they would be unable to shepherd the orbits of the extreme Trans-Neptunian objects. The green line, the yellow line, sorry, uh, it's a limit imposed by WISE, which basically tells us that any object with a mass above 100 Earth masses could be already observed by the infrared survey of WISE. And objects above certain mass and closer to certain semi-major axis would perturb the orbit of Neptune, basically. So that could be ruled out by ephemeris of the orbit that we can constrain very well right now. So the shaded region is basically the space of parameters that still could hide a massive planetary perturber, and the orbit that they are proposing and the mass they are proposing is basically falling in this in the very edge of the shade region. So with this orbit, they made simulations, and basically they observed that objects randomly started at several distances from the sun in the presence of these dwarf planets could be confined. The difference between the longitude of perihelia of the giant planet minus the longitude of perihelia of the test particle would be pretty well confined to where we observe most of the values of the real objects. This is more clearly seen when we observe the evolution of the angular elements in simulations as a function of time. In this case, we did some simulations of the object that we found, which I'm going to talk about a little bit later, and in the presence of this massive perturber, the planet 9. And we see that regardless of where we start the value of the angular parameters of our object, they basically are shepherded by the presence of the additional planet. if we don't have this additional planet, these values simply circulate as it would be expected with only the 4 giant planets. So now we see that in this, coming back again to this work of Nesborny, we see the effect, and we can better understand the effect of an additional perturber in the structure of the outer solar system. So again in this plot, in these A and B panels, we can see the effect that the migration of the 4 giant planets would have on the distribution of the outer solar system. If we only account for giant planets, no galactic tides, no stellar encounters, not anything, we couldn't form an Oort cloud, which is pretty clear here. We could form the structure of the Kuiper belt basically, but we wouldn't have any Oort cloud whatsoever. If we would include just the planet 9 and the 4 giant planets, of course, it's pretty interesting that we can now form actually an overabundance of detached objects that are now shepherded by this planet 9. And in the most complete model that Nesborny et al. Are using, they include everything: planet 9, galactic tides, stellar encounters, and then you can see that you can form the Oort cloud in the most extreme part of the system. You can form a kind of inner Oort cloud, very close to the additional perturber, the planet 9, which is basically shepherded by it, and you can form without any problem objects similar to Sedna. Maybe an overabundance of objects similar to Sedna. But what happened? There's some challenge still. In this paper of 2021, Oldroyd and Trujillo found that another object of large semi-major axis and large perihelia, which is now called Liliaogounhoa, which is this one shown here, TG 387. But because of its large eccentricity, of course, it has a smaller perihelia. But the question is why we have been able to find 3 very distant objects with perihelia above 65 astronomical units, but we haven't found anything inside the red box shown here and called now the gap. In principle, it should be much more easier to find an object that is located in the gap than objects that are far away from beyond the limits of this red box, because they could be much closer to the sun and could be easier to observe. So the argument of Oldroyd and Trujillo in this paper is that this gap, it's actually real, and it's real up to 3 sigma level, up to a 3 sigma level in their models. So essentially, they are fitting a 2 Gaussian distribution to the distribution of observed objects here, as shown in the right plot. So they argument that there are no objects in this region of the phase space of the solar system. How real is this? It's questionable, because if you would found a single object inside the gap that could basically put all this observation to test, right? So it's pretty questionable, but apparently it is real. And what it's very evident is that we have found objects beyond the gap, which are much more difficult to observe than objects that could be in principle in the gap. So what is new? Um, as I mentioned earlier, my colleagues in Asia in Taiwan found a new object, a new extreme trans-Neptunian object, which is interesting not only because of its orbit but because of its colors. Because the colors of this, the color of this object is basically neutral, something that it's couldn't be expected given its low inclination. So it has been known from some years ago that there exists a weak correlation between color and inclination in the Trans-Neptunian region. So the lower the inclination, the redder the color of the objects typically, and this correlation is very strong for the cold classical Kuiper belt, which contains a lot of low inclination objects and which are all of them very red in color. And it's and the correlation continues for other populations, although it's not as strong as for the cold classicals. So this object with very low inclination of 0.48 degrees uh, shouldn't be expected to have this color. So its origin seems to be in other place of the solar system, and that it was put it there by some unknown dynamical path. So if we put 2016 SD106, which we call NARDA internally, we can put it into context um, in the phase space, in the orbital phase space, and it would be located here, just at the extreme of the perihelion distance, uh, inside the gap, not in the gap, inside the gap. So it's still respecting this lack of objects in this observational perihelion gap. And regarding the longitude of perihelion, it seems to be well behaved regarding the the shepherding of an additional giant planet, but not in longitude of ascending node, not necessarily. Put it into context with the most extreme Trans-Neptunian objects regarding inclination. It is the object with lowest inclination among this family, but it also exists. There also exists another object that has a low inclination and has also an extreme orbit that was discovered by the OSOS team and is described in this paper from Bannister et al. In 2017. So this object called SY99 is shown here in the red star, and its origin is explained as a weak diffusion from the inner Oort cloud. So here again, I would like to use my pointer. So what Bannister et al. Did in this paper was put a population of inner Oort clouds objects located initially in this orange square at several perihelion distances, and with same major axis larger than 1,000 astronomical units, and use only the 4 giant planets of the solar system. In very long simulations of 4 gigayears, they found how these inner clouds diffuse in the phase space of semi-major axis versus perihelion, to see if some of these objects can actually be transported from this inner cloud towards the region of SY99. And they found that the blue objects are diffused, are moved from the original distribution by less than 1/4 of the initial semi-major axis. The purple ones are moved a lot more, almost as far as almost as far as the semi-major, as the original semi-major axis of the particle, so almost as much as 1,000 astronomical units. And the red ones are the most mobile of the objects originally put it in this population of inner clouds. So what they conclude is that objects like SY99 are not so difficult transported from a population like the inner cloud by weak diffusion. And essentially, in simulations, one finds that that objects can come and go in a random walk from larger semi-major axis towards inner semi-major to smaller semi-major axis, if only accounting for with only the perturbations from the 4 giant planets. So Narda could be pretty well be another example of this weak diffusion. The problem is again the color. The color is not similar, or is not what one would expect from this kind of objects formed in a different region of the solar system. So in our paper, in our recent paper in 2022, we explored the weak diffusive behavior of this Narda object, and we find essentially what Bannister et al. Found for their for SY99, which is that the perihelia of Narda hardly changes in long-term simulations of 1 gigayear. The inclination has some cycles that do not go beyond 5 degrees in change, and the semi-major axis can diffuse as is expected towards larger values, but most of the particles actually remain close to their original location. Only 8.3% of particles reach semi-major axis larger than 1,000 astronomical units. We can see the same behavior here in the density plots that we use, where basically we plot the residence times of particles in each location of the phase space. In this case, perihelia versus eccentricity, inclination, and semi-major axis. And in the red box, I'm showing the perihelion gap, and in the black line in the bottom panel, it's indicating the stability, the analytical boundary of stability found by Vatican recently, also in 2021, as far as I remember, which only tell us that particles that go above that line are much more quickly destabilized and ejected from the solar system. So if we only consider the 4 giant planets, the diffusive behavior of Narda is pretty well understood. But again, the color indicates that its origin, it's in other place of the solar system. So we explore possible origins for this peculiar object. And the first thing that we did, because the orbital parameters of Narda are very close to the parameters of the hypothetical Planet 9, we include Planet 9 in our simulations and see how this affects the global evolution of Narda and orbital clones of the object. So first we see that the effect of the planet 9 it's very strong in this, again, in these plots of density, of habitability density. And one interesting thing is that the perihelion gap would be highly populated with the presence of an additional giant planet. Also, we would create a lot of large, semi-major axis large perihelion objects that are shepherded basically by Planet 9. So based on the color of Narda, we expect that families that contain objects with similar colors, which are the Haumea family, the Plutinos, and the Tuotinos, could be possible parent families of this object. So we were trying to see if the current solar system, the 4 giant planets of the solar system, were able to produce an orbit similar to Narda from one of these 3 populations. And we find in all cases that the 4 giant planets are unable to transport any object from the inner solar system towards these distances, towards these extreme distances where Narda is located. But a Planet 9 can do it without basically any trouble. At the cost of populating and actually overpopulating the gap, the observational perihelion gap. And this happens in all cases. In this case, we are exploring the possible movement of Haumea family members, here of Plutinos, and the effect of Planet 9 is pretty similar in both cases, and here in the Tuotinos. In all the plots, the black dots indicate the initial conditions of particles, the blue dots indicates the final conditions of those particles, of the surviving particles in the simulations, and the shades of red indicates the habitability, or essentially where particles spend more time during the simulations. And also in all cases, the majority of objects, above 80% of objects, remain in the same locations essentially. So over the black shadow, but the 20% of particles that move are able to reach these orbits that we are interested in. So, in conclusion, we have learned that from the color of 2016 SD106, we expect that its origin is in other place of the solar system. We wouldn't expect this low inclination neutral color object to be originated in place at those regions at those faraway regions of the solar system. So similar colors have been observed in the Plutinos, Tuotinos, and the Haumea family, but we have found that the current distribution of solar system, with only the 4 giant planets, cannot produce Narda-like objects from these families. On the other hand, a Planet 9 can produce these orbits without any problem, at the cost of an overabundance of objects in the perihelion gap. So what are the alternative scenarios here? If we accept that the Planet 9 is present in the outer solar system, we would expect to have already observed objects in the gap with much more ease than the 3 objects already known beyond this limit of the gap. So this seems to be an important constraint on the existence or not of a Planet 9. So the other alternative scenarios are this weak diffusion, that the origin of Narda it's an object that was ejected to the inner cloud in the early stages of the evolution of the solar system, and then the weak diffusion moving back closer to the solar system where we are observing it today. Another possible explanation that I didn't speak here, but has been recently reproposed, is this of rock planets that probably exist at the early evolutionary stages of the solar system that essentially populate in an important manner the um, the outer regions of the solar system, in particular, creating a lot of Sedna-like objects without the need of an additional massive perturber located there now, but that actually was located at the initial stages of the evolution. I think this theory will require that the clustering of of the orbits could not actually be real, which is what all this group of OSUS people and some other groups actually propose, that the apparent gap, that the apparent clustering is also, it's only an observational bias. And in some of our simulations, using the secular perturbations among DPs, their cell perturbations, we have seen that sometimes the perihelion can be risen and stabilized. Uh, in some cases, in very low probability cases, but it's still a possible scenario that we are working in. So I would like to leave it here, and we'll take question if you have. And thank you very much for your attention.
Okay, Marco, excellent presentation. I think you gave a complete overview on the on the problem, and very, very interesting, the features of this object. So now we are open for questions or comments. Anybody would like to make a question or comment? Well, actually, I have one. I was thinking the other way around. If you put, I don't know if probably someone just did that, already made that. If you have if you put objects in the gap, would Planet 9 remove them there from that place?
It's possible, yeah. I guess it's possible. Actually, in the paper of Oldroyd, they made some simulations with different configurations of Planet 9s with different properties. And in some cases, at least in one case, they found that the presence of the Planet 9 could reduce the amount of objects in the gap. So it could be also that that the gap is a direct result of the properties of this external perturber. And yeah, it's possible, and it doesn't mean, the gap doesn't mean to be empty, but it can be very
Low density.
low density populated. Yes.
Yes. Yeah.
Yeah.
Okay. So it's two ways. It can bring bodies to that place and can remove too.
Yeah. Exactly.
Okay. Okay.
Because the transit through that region could be faster. So at any particular time we would see less objects there.
So perhaps a study trying to show, let's say, a kind of steady state could be interesting to do that.
Yep.
Okay, good. So we are open for questions. Anybody else? Any other question or comment? So Adrian, please. Well, okay. Do you want me to make the question? Okay. Adrian Rodriguez Colucci asked, how you investigated the long-term dynamics of the dwarf planets?
Yes, actually, of course. We published the part of our results for the dwarf planets in 2021, last year, from which this result came from. But actually, this result was kind of a side result from that paper, and the main result was the evolution, the particular evolution of the dwarf planets. And yes, we actually divide the evolutions for the stable objects, because most of these objects that are in this blue region are pretty stable over the edge of the solar system. But some of the ones located closer to this dashed line, which is a perihelion of 33 more or less astronomical units, are sometimes very quickly destabilized and actually in some cases ejected. So one of the interesting results we found that was that Haumea, for example, can be lost from the solar system in many cases in less than 1 gigayear. So we classify those kind of objects as unstable or chaotic. And besides that, we have the resonance, where the resonant ones like this, the Plutinos here, and some others in some other resonances. But yeah, I think some of the most interesting cases are the unstable ones, because they not only can be sent outwards, ejected from solar system, they sometimes can send inwards towards the inner solar system and become
Centaur.
a center, yes, or a huge comet, right?
Okay.
And this, well, it's not necessarily only applies to the dwarf planets, but to smaller objects. And we know that centers are very large. So yeah, it's something that it's happening, and we know it's happening. But it can happen to even these very big objects that we would expect to remain there for the edge of the solar system, right? Just because they have a name. Like we have named Haumea, and we would expect it to be there forever, but it's not necessarily the case.
Okay.
Yeah, we published that and we are working on the follow-up papers for different cases.
Okay, good. Thanks, Adrian. Anybody else? Any further question? Okay. So I think that's it. Thanks very much, Mark. I think it was a great talk, very instructive, and you covered a kind of review of the subject. So very good,
Yeah,
very good.
that was the idea, actually, to kind
Very
of.
good.
Thank you very much to you for the invitation. It's a pleasure.
Okay,
And
thanks.
hope to see you soon.
Yeah,
In person.
let's try to arrange that. Okay.
Of course.
Thank you. So now we have just a few minutes to